So welcome everyone to the Asia Pacific Analysis and PDE seminar again. Today, it's a great pleasure for me to introduce Kwok Kun Kwong, who's recently started as my colleague here at the Australian National University. He's going to speak on the effect of average scalar curvature on Riemannian manifolds. Thanks, Kwok.
Thank you, Ben. Thank you, Ben, for the invitation, and thank all the organizers for the great work. I really enjoy this analysis and PDE seminars. Okay, so today I'm going to talk about my more recent work, the effect of the average scalar curvature on Riemannian manifolds. Yeah, so this is the ANU campus. So yeah, welcome to visit us anytime. So this is based on my archive preprint with the same title. You can find on archive. So so first some notation. In this talk, N will be a complete Riemannian manifold. So equipped with a Riemannian metric G, which I assume to be smooth, and often I assume is actually closed, meaning compact with our boundary and orientable. But anyway, so there are three very common curvatures in Riemannian geometry, namely the sectional curvature, the Ricci curvature, and the scalar curvature. If you are already a geometer, I'm sure you already know the definition, but let me just briefly describe them. So the sectional curvature, or the Riemannian curvature tensor, is basically the commutator of the covariant derivative. So it can be computed like this. But the exact formula is not extremely important in this talk. But this is among these three, this is the strongest one. So theorem assuming a bound on the sectional curvatures are really very strong assumptions. So usually we instead assume some bounds on the Ricci curvature or even scalar curvature. So the Ricci curvature is actually the average of the sectional curvature in some sense. So this is a Q tensor, which I write as Rij, and this is nothing but just taking the trace of the sectional curvature with respect to, let's say, the last and the first indices. Okay, so as an average, of course, it's a weaker curvature. I'll explain the geometric meaning of the Ricci curvature and also the scalar curvature later on. And if you take another average, so if you take the average over all directions, then you get the scalar curvature. So on the manifold setting, it's just a function on the manifold. So this is exactly taking the trace of the Ricci tensor. So or in other words, just take this combination G upper Ij times Rij. So of course, so scalar curvature being the average of the Ricci curvature is the weakest one. It's the weakest among all these curvatures. So there's very little that we can say assuming a lower bound, for example, of the scalar curvature, because it's just a kind of average. All right. So so the talk. So the main theme of this talk is, roughly speaking, just saying that when we have large curvature, then we will have some small size. But what does that mean by large curvature? Which curvature are we using, and what size are we referring to? Right. So let me just briefly describe the geometric meaning of the Ricci curvature. So that's not the only geometric meaning. So there are several different interpretations, but this one seems to be more geometric. So let's say so we can actually fix a certain direction at the tangent space at P. So let's say we have a fixed point P, and then there's a certain direction theta. So so if we shoot a geodesic, or if you like, a light ray around this direction theta, then so it will just trace out a cone, and we measure this cross-section area of the cone. So so in some sense, if the Ricci curvature at this point P and in this direction theta is 0, then more or less the cone area is just the ordinary one. So it's just more or less the Euclidean cone area. But if the Ricci curvature is positive in this direction, then the light ray or the geodesic will start to converge somehow, and the area is actually smaller than the Euclidean one. And if Ricci curvature is negative in this direction, then the light ray will kind of diverge, and then the area is actually bigger than the standard one. So that's one geometric meaning of the Ricci curvature. So in mathematical language, what I have described is just this statement here. So you can see the main term is r to the power n minus 1, referring to the Euclidean area. And then the first correction term is the Ricci curvature, actually minus the Ricci curvature. Okay, so so that's the geometric meaning of the Ricci curvature. It depends on the direction. And that's a very similar geometric meaning of the scalar curvature R. So we call this is a function, the scalar curvature function. So so what it means geometrically is the following. So let's say you fix a point P, and then you look at the volume of the balls with radius r, and you measure the volume. Then so it turns out for small r, then let's say if the scalar curvature is 0, then the volume of the ball is more or less like the Euclidean, so basically r to the power n. And then if the scalar curvature is positive, then the volume of this ball, small ball, is slightly smaller than the Euclidean ball by this factor here. So we have a correction term of r to the power n plus 2 multiplied by negative of the scalar curvature, basically. And then if the scalar curvature is negative, then the corresponding ball is bigger. Okay, so this actually can be taken as the definition of the scalar curvature. Although in practice, we don't usually use this definition because we really can't compute things using this kind of definition, but instead we just use the trace definition. So so with these pictures, we can already see that the scalar curvature tends to oppose the growth of the volume of balls, at least for small r. So that means if you look at this Taylor expansion, then you can see that if the scalar curvature is positive at a certain point, for example, then the volume of the ball is strictly less than the Euclidean ball. Okay, at least when r is small enough, right? But you can't actually overgeneralize this statement, because you can't say that, oh, how about if the scalar curvature is non-negative? Let's say it's greater than or equal to 0. Is it true that this volume is less than or equal to the corresponding volume of the Euclidean ball? Well, it turns out it's not true. So it's not that easy. And the simplest kind of example is the simplest kind of example where r is constantly 0. So it's the unit sphere times the hyperbolic plane, which has sectional curvature -1. So if you compute the scalar curvature, so it turns out it's exactly the scalar curvature of this vector plus the scalar curvature of this vector. So it's multiplicative or additive in this sense. So they cancel each other, and the scalar curvature is 0, right? But but then if you look at the volume of the balls, then actually you have a certain Taylor expansion. So notice that in this case, so this is a 4-dimensional manifold, but then the next non-trivial term is actually of r to the power 8, because that term consisting of the scalar curvature just vanishes, right? So it turns out the next non-trivial term is r to the power 8, and that factor turns out to be a positive factor, right? So it's 1/3000 something, I guess. So it's just slightly bigger actually than the Euclidean ball. It's slightly bigger than the Euclidean ball, although it's very close. So they compete with each other. The sphere compete with the hyperbolic plane, and it turns out the hyperbolic plane wins by a very small margin. Okay, but it's still a win, right? So it's close to, but not really smaller than or equal to the Euclidean volume. So as a first lesson, that means the scalar curvature alone, the scalar curvature lower bound alone is not enough to say anything about the volume of the geodesic balls, even for really, really small balls, right? Really, really small radius. So if we want to do a volume comparison involving the scalar curvature, so you just can't assume a scalar curvature lower bound alone. And you may also wonder why I always talk about the scalar curvature lower bound instead of, for example, upper bound. That's because the upper bound of the scalar curvature is often not very useful to deduce anything topological or even geometrical, at least when the dimension is at least 3. That's because any manifold, any 3-dimensional or higher than 3-dimensional manifold has actually a complete metric with even Ricci curvature being negative. Okay, so this is a result of locam. And if this the Ricci curvature is negative, then of course the scalar curvature is of course also negative. So it has already an upper bound. So there's nothing that we can say about this manifold because this manifold is just arbitrary. And also actually Oban already got this result with the scalar Ricci replaced by the scalar curvature using a conform move method. So so they proved that basically an upper bound of scalar curvature doesn't have much to say about the topological structure of the manifold. Okay, so so as I described, the scalar curvature is pretty weak, and you can't really have much control for manifold with some bound of the scalar curvature. So let me just directly cite Gromov's viewpoint about this situation in his 4 lectures on scalar curvature. So that's directly his. So he described this situation like this. So there's no single known geometric argument which make use of this definition. So by this definition, I mean he means this geometric definition of the scalar curvature. And then he described that the immediate reason for this is the infinitesimal nature of the volume comparison. So just remember the previous pictures. So this property doesn't integrate to the corresponding property of balls of specified, but maybe even small radius r, right? So in his opinion, we can't really integrate the infinitesimal nature of the volume compression. All right, so and then he follows up with a basic question: does the sign of the scalar curvature have any visible macroscopic? So let me emphasize the word macroscopic. So we want something in a large scale on the geometry of the manifold. So in my setting is n. Let's say scalar curvature has lower bound k. Let's say positive k. Then what can we say? So that's his viewpoint. So in this talk, somewhat contrary to his opinion here, I'll describe a way to kind of integrate the volume comparison property of the scalar curvature. But of course, we can't just assume the scalar curvature lower bound alone. So the situation is actually quite different for the Ricci curvature tensor. So that's the quite famous Bishop-Gromov volume comparison theorem, which says the following. So if the Ricci curvature has a certain lower bound, then if we look at the volume or the volume elements actually, so let's say the volume form can be written as the Jacobian F times the r d theta, where r and theta are the polar coordinates. Then we actually have a volume comparison theorem, and actually that's I'll call it volume elements comparison theorem because we already have the volume elements comparison. So for the Jacobians, so the Jacobian or volume element is less than or equal to the standard one. So for example, in the flat case, the volume element is r to the power n-1, and so on. So if we integrate, then we get the volume comparison for the balls. So the geodesic ball is smaller than or equal to the space, the ball in the space form. So now a natural follow-up question is that, let's say we have Ricci curvature lower bound, and then the scalar curvature, let's say non-negative Ricci, and then the scalar curvature lower bound is actually better than taking the trace of this inequality. Let's say R is bigger than or equal to a positive number C. Then actually, can we improve Bishop-Gromov, right? So can we actually improve it? Because even if this Ricci curvature is only known to be non-negative, that the scalar curvature is actually bigger than 0. So can we say that the ball is smaller than the standard one minus something? So in exactly this setting, I still don't know the answer. Although there are some work, for example, by Friedman and Brown on the homogeneous space, for example. But in their result, they are not exactly using this assumption, but they can kind of improve the Bishop-Gromov estimate for homogeneous space, for example. And that's another famous conjecture by Gromov, which says that if n is complete non-compact and not with non-negative Ricci curvature, and suppose the scalar curvature has a positive lower bound, then the volume growth is basically at most of the order R to power m-2. Okay, so this is still open, but there's some work quite recently by Beaujeu under some non-collapsing assumptions on volume. He is able to prove this kind of theorem, but this is about non-compact manifold and about volume growth rate of the balls. But let me show you a somewhat surprising result, which is quite surprising to me because even the average of the scalar curvature, so scalar curvature is already pretty weak, but then the average scalar curvature is even weaker. So a result by Green and independently by Berger actually made use of just the average scalar curvature to say something about the size of the manifold. So the statement is that if n is a closed manifold and the average scalar curvature is at least n times n minus 1, doesn't really matter, so it has a positive lower bound, then the corresponding conjugate radius is at most pi. So pi is exactly the conjugate radius of the unit sphere, and the unit sphere has scalar curvature, or actually constant sectional curvature, exactly n times n minus 1. So by the conjugate radius, it means basically that let's say conjugate radius is r, then that means for any geodesic of length r, there isn't a pair of conjugate points on that geodesic. Or in other words, the exponential map is actually non-degenerate within a ball of radius r. Okay, so this is the largest such r. So in some sense, this conjugate radius measures the size of the manifold. So it says that the average scalar curvature is big. In some sense, then the size is small. So I think the significance is that even such a weak notion, our bar can say something about something topological, something about the size, something global. Okay, so this is I think the significance. So so let me show you the idea of Green's or Berger theorem. So it is basically a clever use of index lemma and together with the Liouville's theorem. So the proof is the following. So let me zoom. Okay. Right. Okay. So let's say we have a geodesic of the length L, which is the conjugate radius. So now what we want to do is to bound the conjugate rate to bound the length L here, right? So let's choose these test vector fields xi, so which are actually just the Jacobi fields on the sphere, okay, sine pi t over L times EI. So it's just the Jacobi field on the in the model case. So where EIs are parallel orthonormal frame along this geodesics. So we can choose n minus one of them. Okay, so now we can apply the so-called index lemma. So what's the index lemma? Index. So first of all, the index form I is nothing but just the second variation of the energy. So that means the integral of the square of the speed of the geodesic. So if we differentiate twice with respect to the parameter, so let's say we have a family of curves or geodesics, then we get the second variation, and it's a quadratic form, which is called index form, so denoted by I. So it turns out the formula is given by this integral here, right? So basically the energy of the vector field minus a curvature term. So you'll notice that this is the sectional curvature. So if we take the trace, then we'll get the Ricci curvature for this term, because Ricci is the trace of the Riemannian curvature tensor. And so this term we can actually compute it very explicitly. So this, up to this step, this is very similar to the Bonnet-Myers theorem proof. So, but then this is the Ricci curvature, not the scalar curvature. So the next step is really ingenious, I think. So what he did is to integrate over all p and theta in the unit tangent bundle. So what does it mean by unit tangent bundle? Is just the collection of all the unit tangent vectors in the manifold. Okay, so if we take this geodesic gamma to be parameterized by p and theta, where p is the starting point and theta is the initial direction, then we can regard this as a family parameterized by the unit tangent bundle of unit length geodesics. Okay, so now we integrate over all p and theta. So that means over all directions. So if we integrate, so we are integrating over the unit tangent bundle. And now because everything is compact, we can safely interchange all the integrals. So now we integrate with respect to the p theta first. So what will happen is the following. So we integrate with respect to the p and theta parameter first. And then we'll make use of the fact that the so-called geodesic flow actually preserves the standard measure in the unit tangent bundle, which I denote as d mu Sn. This is called the Liouville's theorem. So what is the geodesic flow here? So if we start from this direction theta, so if we flow along, if we shoot a geodesic with this direction as the initial direction, and then after time t, so it will go to this point, and the tangent vector at this point is just gamma dot at time t. So if we map this theta to this tangent vector, then this is the geodesic flow. And it's easy to see that because geodesic is obviously preserving the speed. So this is, if we start from a unit tangent vector, then this is also a unit tangent vector, although they are based at different points. So we can regard this as a flow in the unit tangent bundle, right? From a unit tangent vector to another unit tangent vector. And the nice thing about this geodesic flow is that it preserves the measure, the mu of Sn. Okay, so let's continue the calculation. Okay, so we are concentrating on this integral here. So we have swapped the integrals. So we integrate with respect to p and theta first, and then with respect to t later. But now making use of this Liouville's theorem, so we can put it back to the initial point. So this gamma dot t here will just become theta. And we are integrating with respect to p and theta. So now we can do a little bit more. We can integrate along the unit tangent space at p first. That means all the directions starting from p, and then integrate with respect to p as a second step. So this will give you the scalar curvature at the point p, because we are integrating with respect to all directions. That means basically taking the average at the point in the tangent space at P. So that will give you the scalar curvature. So that's why we can just assume the average of the scalar curvature, because if we integrate with respect to P, then this is exactly the average of R. And we have assumed a certain lower bound of the average of R, so replace it by the lower bound. So that will give you this inequality here. And if you rearrange it, this will give you exactly an upper bound of L, which is the conjugate radius. Okay. So that's the whole proof. So it makes use of the index lemma. So the index lemma is applicable if we are within the conjugate radius. That means if there's no conjugate point, then we can actually apply this index lemma. So the index lemma is basically saying that as long as there are no pairs of conjugate points on the geodesic, then the energy is actually minimizing on this geodesic. So the second variation is actually non-negative. That's exactly what the index lemma is saying. Right. So we have used the index lemma and Liouville theorem to prove something about the size. And if you look at the proof again, this is actually a statement about average conjugate radius, if you like. So with this in mind, I consider the problem of whether we can make use of this argument to deduce something about the size of the balls or the size of the spheres, geodesic spheres. So so it turns out if the Ricci curvature, for example, is non-negative and the manifold is closed, then we can say something about the average volume of the balls. So the average volume of the balls, denoted by V bar, is actually less than or equal to the Euclidean volume minus a certain correction term, which looks kind of complicated, but very explicit. So here R bar is the average scalar curvature. Sorry. So if the R bar is positive, then actually this term is positive because this integrand is actually non-negative. I think it's actually positive. So we have an improved bound of the Bishop-Gromov volume estimate. So the equality holds if and only if the manifold is flat. That means locally it's just Euclidean, and the radius is less than or equal to the injectivity radius. Okay, so the injectivity radius is the largest radius to make sure that the exponential map is always a diffeomorphism at every point. So so actually I can do it slightly better. So the Ricci curvature bound can be anything. Lower bound can be anything. It can be a negative number or a positive number. But then this integrand has to be modified. So for simplicity, I just give you the version where Ricci curvature is non-negative. Okay, so and it's consistent with the previous observation that we can't just assume scalar curvature lower bound alone. We have to, for example, assume something about the Ricci curvature, and that's what I can obtain. So similar results hold if this modified Ricci curvature has a lower bound. So if n is compact, then of course the Ricci curvature has a lower bound. So so if the lower bound is k, then this modified Ricci curvature Ricci k is non-negative. And let's say it has also an upper bound kappa, which of course it has. Then there's also a similar result. So as a particular case, so if let's say this small k is 1, then the Ricci one is non-negative and bounded above by kappa. Then we have such an upper bound for the total volume of the manifold. It's more than or equal to the volume of the whole sphere minus some correction factor involving the average scalar curvature. And again, so this is again something positive. So I didn't write down what's the definition of sigma 1 here, but this is something very explicit. So anyway, so and this inequality is sharp, and it holds if and only if the equality holds if and only if it's just a sphere, right? So the ingredients are more or less also the Liouville theorem, but I also need some more, which is one of them is the Jacobian estimate. without any Ricci curvature lower bound. And the second one, and another one is the, I call it reverse Jensen inequality. Okay, so this is pretty elementary inequality, but turns out to be useful. So let me talk about the first ingredient, the Jacobian estimate in the flat case, for example. So again, F is the Jacobian in the polar coordinates around a certain point P. So the estimate I have is this one. Okay, again, very complicated thing. But let's just get some feeling of this estimate. So what is it talking about? So so if the, let's say, Ricci curvature is 0 or is non-negative, then the whole thing inside the square bracket becomes 0 or bounded above by 0. Then exponential of 0 is just 1. Okay, so in this case, it's just saying that F is bounded above by r to power n minus 1, right? R to power n minus 1, and that's exactly the Euclidean Jacobian. And another thing I want to emphasize is that there's no assumption on the Ricci curvature, right? So that means actually this Jacobian estimate is true for any manifold as long as you are within the injectivity radius. Okay. So outline of the proof. So if we have again a geodesic starting from P and shooting in the direction of theta initially, then again we take a certain orthonormal frame EI from I from 1 to n, and then we take the Jacobi field YI such that at the endpoint is exactly EI. Okay, so there are n minus 1 of them. So why do we care about the Jacobi field? Because we can use them to compute the Jacobian. So it turns out basically the determinants of all those Jacobi fields basically normalized by the initial velocity. So if we take the log differentiation with respect to r, then it's not too hard to see that it will give you the index form. Okay, so this is basically because if we differentiate the determinant, you get the trace, and so you see the sum. Okay, sum of something. That something turns out to be the index form. So so if we differentiate log f, then we get the sum of the index form, sum of I of yi. So now we want to make use of the index lemma. So we have to choose a certain comparison vector fields, and the comparison vector fields X has to agree with the Jacobi fields at the two endpoints. So the most natural ones to choose in the flat case is just linear vector fields. So basically, R is constant, so this is basically T times EI. So choose XI to be something like this. And then, so if you look at this expression, so everything is very explicit. So you can just directly compute I of XI, and you get something like this, right? So you can see the Ricci term and the main term here. So this is the main term because this is the basically Jacobian in the standard case, r to power n minus 1. And this is the error term because it tells you how it deviates from the standard one. So you have, using the index lemma, you can compare the two expressions. And then if you integrate back with respect to r, then you get the this expression involving the exponential function, right? So that's how we get the Jacobian estimate without any assumption on the Ricci curvature, because that's what I need. If I assume already a Ricci curvature lower bound, then that won't be too useful. Okay, so so this is the error term here, and if I integrate the error term, that's the correction term here. So that's the first step. The next step is obviously to integrate with respect to r and theta. Okay, so but the problem is that, of course, you want to integrate such that you can make use of the Liebow's theorem. Okay, so if you can actually integrate around with respect to p and theta like this, then you can cook up the term scalar curvature. You can cook up the the scalar curvature R here. But you can't really do this because there's an exponential function here, right? So there's an exponential function. You can't really just put the integral sign inside the exponential function. So that's why I need to get some. I need to derive some reverse Jensen inequality. Okay, the Jensen inequality is not helpful here because the inequality sign is exactly reversed. So this is a pretty simple lemma. So which says the following. So if f is bounded above and below, and if we want to get an upper bound of exponential f on a probability space, for example, then it turns out to be bounded by some linear integral like this. Okay, so sorry about that. Okay, so somehow I want to put the integral in front of the f, but instead I upper bound this integral by this linear integrals instead. Okay, so the idea is pretty simple. So we have exponential function e to power y, and we know that y is in between m1 and m2. So we can replace this function by an upper function, an upper bound ay plus b, where the two endpoints have exactly the same values on the graph. Then you just replace the integral of e to power y by ay plus b, where a and b depends on the upper and lower bounds of the function. Then you integrate, you get something like this. Okay, so pretty simple idea. So let's see how we can apply it. Right, so now let's take the probability space to be the unit tangent bundle, normalized by basically the total volume. And the function that we want to integrate is actually the Riemannian. Okay, so remember the Riemannian curvature depends on the direction, and actually there's a base point P. So you can regard this as a function on the unit tangent bundle Sn, so Riemannian of P theta, and assume that the Riemannian curvature on this unit tangent bundle has a lower bound and also an upper bound. Then we want to integrate this inequality that we derive from the step one. So if we integrate on the left-hand side, we get basically the average area. So nothing special here. Now on the right-hand side, we want to swap the exponential and the integral sign, but we can't really do it directly. So we'll have to make use of the lemma. So we can only put the integral sign here like this. Oh, I can write on it anyway. So so we can apply the lemma. Where's the pen? Okay. So so we can apply the lemma, and then we can convert the bound into something like this. So basically, we put the integral sign in front of the Riemannian curvature. Somehow the pen is not working. Just a second. Anyway, so so we put the integral sign in front of the Riemannian curvature like this. So the point is that if we can do it, then we can cook up the term scalar curvature. Sorry about that. There's some problem with my computer. Can you see the screen now?
Yeah, I can see it fine, but I can't see the pen now.
Yeah. There's some problem with my computer. Anyway, I'll use my mouse instead. Okay. Sorry. Yeah.
The sharing stopped. Yeah.
Yeah. There's something wrong with the OneNote app. Do you see it now?
Yeah, that's good.
Okay. So let me continue. So we apply the lemma and then put the integral sign in front of the Riemannian curvature. So the upshot is that it will cook up the term the scalar curvature, and that's good because that's exactly what we want. So we now have an expression which is an upper bound for the average area in terms of the average scalar curvature, right? So so if we integrate again, so this is the average area of the geodesic sphere, and then if we integrate with respect to R, then we get the upper bound for the average volume, and then turns out to be this expression here, right? So we can only talk about the average because if we apply the geodesic law, then we are already taking the average. So I don't know anything that we can say about the exact volume of a certain ball, even if we know everything within this ball. But somehow I can use the geodesic flow to say something about the average. But I'm still quite happy because the scalar curvature appears in this expression. There's also some similar results regarding the average mean curvature of the geodesic spheres. So in one of the steps above, I derived this inequality. Okay, so let's call this star. So in the previous proof, I integrate with respect to r first, and then integrate with respect to p and theta. But then if I integrate with respect to p theta first, that means along all the directions, and then apply the Liouville's theorem, or I call it Green's trick, then it turns out to be an expression like this. So this can be regarded as a certain monotone quantity, because on the left-hand side, I don't exactly know the meaning, geometric meaning of this integral. But on the right-hand side, this is just basically this average scalar curvature. So if the average scalar curvature has a sign, let's say non-negative, then it will become a decreasing quantity. So I think this is quite interesting. And also this can be regarded as the mean curvature comparison, but in the average sense. Okay, so the mean curvature of the geodesic sphere can be actually regarded as the log derivative of the Jacobian f. Okay, so if you observe this, then you can just regard this as the mean curvature comparison, but in the average sense. So HP r theta is the mean curvature of the sphere centered at P with radius r, and then we take the average over all P and all theta. All right, so it turns out to be less than the corresponding mean curvature of the Euclidean sphere. So the Euclidean sphere has mean curvature m-1 over r, and that's a correction term in terms of the average scalar curvature. And notice that in this theorem, I didn't assume anything on the Ricci curvature. So that's quite nice. So in the above theorem, I assume a Ricci curvature bound, although the bound can be negative or positive. So I still have to assume something about the Ricci curvature. But in this theorem, I didn't. It's just directly from this estimate here. The reason is that I didn't need to use the reverse Jensen inequality, which assume a bound on the integrand. So I just integrate everything. It's just straightforward. I didn't assume the Ricci curvature lower bound. And then there's a more general version for general K, but I guess this is more or less the same. So this is also quite surprising to me because Gray and Van Heck, they proved something like this. They basically compute the mean curvature integral with respect to theta. So it turns out for small r, the theta expansion is something like this. Okay, so somehow this result agrees with my result, because if you look at the first term here, first correction term, if you take the average, this is just r bar. So this is without the average over p. But then the next term becomes more complicated, but you can still integrate, and you'll see that actually this is a positive quantity. That's okay. But then the next term is really, really complicated. They computed the exact value of this r to power 5 term, but it spans 3 lines. And I don't think there's an obvious sign. I don't believe there's a sign for that term. So their computation is really quite amazing. So I mean, I'm very impressed by their calculation. I don't think I can do something like this. But anyway, so yeah, it's a very complicated term. So you can't really say that, oh, yeah, let's just integrate and then get this inequality here. No, you can't do this because there's no sign for this term here. So and so I'm quite happy with this bound here. So there's no assumption on the Ricci curvature, and it's much cleaner than this theta expansion here. I think that's the last result I just want to mention, but I'm not going to prove. I can also say something about the eigenvalue. which is a generalization of Jan's eigenvalue theorem. So his theorem is that if we have a Ricci curvature lower bound, then there's an upper bound for the eigenvalue of the geodesic force. So it's actually bounded above by the eigenvalue. By eigenvalue, I mean the first eigenvalue for the Laplacian operator, okay, with respect to the Dirichlet condition, okay. So so his result is without this complicated term here. So the so lambda 1 is actually less than or equal to lambda 1 of the ball in the space form. So my result also has to assume a lower bound of the Ricci curvature, but unfortunately, I also need an upper bound of the sectional curvature for some technical reason. But anyway, so if it's closed, then of course it has an upper bound, but somehow I want to get rid of it, but I'm unable to do so. But anyway, so the conclusion is that we can actually improve his bound by such a complicated thing, but everything is explicit. So this phi here is actually the eigenfunction in this space form, but I don't want to write down the exact expression. I don't think there's an exact expression anyway. But so this improves the Jan's eigenvalue estimate, and this is also sharp. The equality holds if and only if the curvature is constantly k. So that's all the result I want to I want to tell you. But there are some questions that I have in mind, and I don't know how to answer at this moment. So the first question I've already actually mentioned. What does that monotonicity quantity mean, or does it imply anything, or is it actually known? So the quantity is this quantity here. So I'll say this quantity looks like a comparison between the Jacobian and the standard one, but there's a log to it. Okay, so of course you can replace it by log f minus log of r to the power n minus 1. But then what's the geometric meaning of this quantity? So this is a monotone quantity if the scalar curvature is non-negative, for example. So I don't know what's the exact meaning except this mean curvature compression. Okay, so that's one question in mind. So maybe not a very major question, but anyway, I'm curious. Maybe the more serious question is about non-compactness. So you can see in the above results, I always assume compact manifold, and it's compact. That's because I need to make use of the Fubini's or the Tonelli's theorem. I want to swap some integrals. So if your space is non-compact, there may be some issues. Actually, I can relax it to somehow to the setting where the volume is finite, but with the I think the negative part of the Ricci curvature is finite, then we can also do something. Yeah, I mentioned it here. Okay, so if the negative part of the Ricci curvature on the unit tangent bundle is finite, then and the volume is finite, then somehow I can still make use of the Fubini's theorem and carry out the same proof. But then in general, that may be too much an assumption. And also if the volume is infinite, somehow you have to be very careful about the average. What does it mean by average of the Ricci curvature or the scalar curvature when the volume is infinite? Well, for nice enough manifold, so you can still use the limit to define the average. But in general, you have to be slightly more careful. Some other settings, like with boundary, I don't know. So this may be that may be interesting because let's say if you think about the positive mass theorem, which also is a result involving the scalar curvature. So nowadays there are many positive mass theorem even with boundary. So you may assume maybe some mean curvature assumption in the outermost boundary or something like that. Then you can still prove positive mass theorem. And Kähler setting and also Lorentzian setting, they may be so yeah, they are also quite interesting because some time ago I did a Ricci curvature compression involved on a scalar manifold. And for Lorentzian settings, so those compression theory is actually related to the singularity theorem of Hawking and also Penrose. So there may be some interest, some physical interest for results of this kind. But this is, I think, this is the hardest setting, because in the Lorentzian settings, the unit sphere is not compact. So you have the unit sphere in the light, inside the light cone, so it's actually non-compact. So it's hard to say something about the average scalar curvature or average Ricci on the sphere or something like that. So if you are doing something like integral on the unit tangent bundle in the Lorentzian setting, I guess there must be a lot of technical difficulties you have to overcome. So that's the end of my talk. So thank you for coming.
Thanks, Kwok. Very interesting talk. Okay, so if anyone has questions, feel free to raise your hand or post the question in the chat. Either way is fine. And I also want to remind everyone that in the email that you all received advertising the talk, there's also a link to a coffee break, which is just a chance to have a chat with Kwok and with whoever else would like to come along. So everyone is welcome to that. We'll do that in a few minutes after we've finished questions here. So one quick so you mentioned this question about the non-compactness.
Yeah.
Is there anything you can say, for example, in the setting where you might have an asymptotically flat manifold? Does that give you enough control to say anything extra?
Yeah, well, for the time being, I don't know, but that's maybe true, because the scale curvature is kind of decaying. So I think in this case, you may be able to make sense of the average, something like that. But I haven't worked out the details.
Yeah, I guess in that case, it seems likely the average might be zero, but maybe you would need some more information about the K rate or something.
So if the scale curvature is L1, which the positive mass theorem usually assumes, then of course the average is zero. But there may be some other cases. I don't really know. And in the paper of Friedman and Brown, they seem to also have some analysis regarding the volume of balls in a manifold with infinite volumes. So average volumes of the balls. So they have to, but their assumption is different. In particular, they don't assume anything about the scale curvature, but they have a version of the enhanced Bishop-Gromov theorem on arXiv, which is quite interesting, but the approach is different. A similarity is that they also make use of the geodesic flow, the Neufield's theorem.
Yeah. So one thing that's interesting is that you make a very weak assumption on the scalar curve, just the average.
Yeah.
And then your conclusion is somewhere also weak. It just says, somewhere something goes wrong.
Yeah.
On average.
Yeah.
Whereas
I was.
If you take pointwise bounds, then you get something much stronger, of course.
Yeah.
Is there some way? I mean, it'd be nice to be able to somehow interpolate between these two extremes and get some condition which gets you partial information in between.
Yeah.
I don't know how that would work.
Yeah.
Sorry, you were going to say something else.
No, you said two extremes. So which two extremes are you referring to?
Well, I mean, one extreme where you have pointwise inequality on Ricci curvature or scalar curvature, and they give you something saying that everywhere you have resulting inequality on the volume. Whereas with your average, you get simply more or less a statement that somewhere there is a ball with small volume, or along those lines. I'm just thinking how you could formulate something which is somehow in between these two.
Of course, the weakness of my result is that I can only say something on average. So on average, the ball is small, but maybe there's a very large ball.
That's right. Yeah. So there's somewhere, and like in your example with you had the inf of the the lambda
yeah.
ones over
Yeah.
balls.
That's also the weakness, because that's exactly the same problem. So because
Sure.
I can only say something, there's something wrong with my OneNote. Anyway, because I can only say about actually the average of the eigenvalue in some sense. That's why I need to impose that condition.
Yeah, that's right.
Yeah.
Anyway, I mean, it works out very beautifully. Yeah.
Yes.
Okay. Does anyone else have any other questions? It looks like there's nothing in the chat as far as I can see. So if that's the case, then let me just thank you again for a very interesting talk, and reiterate that everyone is welcome to come along and chat at the coffee break.